Okay, in this video we are going to discuss what is known as kinematic inversions. So we have defined what's mechanism earlier, that it's a closed kinematic chain with one link fixed. Okay, so in the same kinematic chain, if I fix another link instead of the previous link, then I will get totally a new mechanism, and that new mechanism is the inversion of the earlier mechanism. So just by changing the fixed link, we can obtain different mechanism for the same kinematic chain, and that is known as kinematic inversions. Okay, so let's see some example. So first let's take a very simple kinematic chain. So this is the kinematic chain where it's a 4-bar mechanism with 4 revolute pairs. So all kinematic pairs are revolute pairs. Okay, now in this one, if I fix this this link, then I will get one mechanism. Okay, instead of this, if I fix link 2, then I will get this mechanism. Okay, and similarly by fixing link 3, I will get this mechanism, and by fixing 4, I will get this mechanism. Okay, but for this mechanism, everything looks very similar, right? So it doesn't look like different mechanisms. But at the same time, instead of one of the revolute pair, if I change that into a prismatic pair, we will get a very different inverse mechanisms. We will see that. Okay, so this is this is link 1, this is link 2, and that's link 3. Okay, and this is link 4. And now if we fix link 1, we will achieve this mechanism. Okay, and this mechanism is known as slider crank mechanism. So in this slider crank mechanism, by rotating this link 2, we will get an linear oscillatory motion at link 4. Okay, and instead of 1, if I fix link 2, what I will get is this one, and this is known as quick return mechanism. Okay, so in this quick return mechanism, the link 3 will be rotated, will go through a complete rotation, where the link 4 will have a to and fro oscillation. Okay, rotary oscillation, and in this oscillation, if you see, it will go very fast in one direction compared to the other direction. Okay, in certain cases that will be used, and since while going forward it will go slowly, and while coming back it will come quickly, and therefore it is called quick return mechanism. Okay, and if we fix link 3, we will get a mechanism which is known as oscillating cylinder engine mechanism. Okay, now I want you to think what will happen if we fix link 4. What will happen if we fix link 4? Okay, what you will achieve is the mechanism which you will observe in the hand pump. Okay, so I want you to just observe the mechanism in the hand pump, and just see whether it's an inversion, whether it's an inverse of this mechanism or this kinematic chain. Okay, fine. Now what we are going to do is, what if we replace one more revolute pair into a prismatic pair? Okay, so what we will achieve is a mechanism which looks like this. Okay, so if you see here, this is a link 1 which is fixed, this is link 2. Okay, this one is link 2, and those two things are connected using a revolute pair, where this thing is link 3, and link 2 and link 3 are connected using a revolute pair, where link 3 and this whole thing is link 4. Okay, link 4 are connected using a prismatic pair, and link 4 and this one, which is again link 1, they are connected using prismatic pair. Okay, so it has, for example, if it's a let's call these boxes as link 1, link 2, link 3, link 4. Okay, where link 1 and link 2 are connected using a revolute pair. So the first revolute pair, let's call R1, and the link 2 and 3 are connected once again using revolute pair, so let's call R2, and link 3 and 4 are connected using prismatic, so maybe let's call P3, because here they have denoted like this, and the 4 and 1 are connected once again using prismatic pair, so we'll call that as P4. Okay, so in this mechanism we have fixed link 1. Okay, by the way, this mechanism is known as Scotch-York mechanism. I think, let me make sure the spelling is right. Yeah, so Scotch-York mechanism, and right, so that's one thing, and it may look like so finally, by having an oscillatory motion, we are complete rotation, we are achieving a oscillatory straight line motion, which looks like very similar to slider crank mechanism, but there is a difference which we will learn when we learn the displacement analysis. Okay, and instead of 1, what will happen if we fix link 2? Okay, so what we will achieve is, so instead of 1, if we fix link 2 like this, what we will achieve is this mechanism. Okay, so yeah, it looks complicated. Maybe I'll do one more thing. So even this picture looks complicated, so what I could do is, I will reduce some details and put some kinematic diagram. So this is our fixed link. Okay, and that fixed link is connected with link 2, say this one, and here we have link 3, and link 3 is connected with link 4, where this is a single link, so let me put it like that, and we have slider, and also this is also fixed and it's moving in link 1. So this is link 1, 1, this is 2, this is 3, and this whole thing is 4. Okay, maybe instead of this picture will give you more clarity. Okay, so when you do the inversion, okay, maybe with that understanding, I want you to check this mechanism, and in this mechanism, if this mechanism will be achieved if we fix link 2. Okay, and this mechanism is known as Olam's coupling. So what we will achieve is the rotation of a shaft or this link 3, okay, will be converted into a rotation once again, but in a different axis. So these axes are different. So that can be achieved. Okay, so this is known as Olam's coupling. Okay, so in this kinematic chain, instead of 2, if we fix link 4, okay, what we will achieve is the following. This is the mechanism which we will achieve, and this mechanism is known as elliptic trammell. Okay, so the reason it's been called elliptic trammell is because, so in this mechanism, if we see, so link 4 has been fixed, okay, and this is link 2, and this is link 3, and this one is link 1. Okay, this slider is link 1, and this slider will move to and fro with respect to link 4, and link 3 will move to and fro, but in this direction with respect to link 4. And link 2 has been connected such that while these two things are moving, while the link 3 and link 1 are moving, link 2 will move such that this particular point, the point D, will trace an ellipse. Okay, so that's why it's called elliptic trammell. Okay, so how can we say that that particular point trace an ellipse? Let's see. So let's say this is our origin of the coordinate system, in which this line is the x-axis and this line is the y-axis. Okay, in that case, what is the point? So let's see, what is xd? xd is AD into sine theta. So this is the theta. Okay, so xd is nothing but AD sine theta, and what is yd, which is CD, okay, C to D cos theta. Okay, now from this what we can say, let me rewrite that such that sine theta is equal to xd by AD and cos theta is equal to yd by CD. Okay, now we know from our trigonometry identity that sine square theta plus cos square theta is equal to 1. So if I use that, then what will I get? xd by AD square plus yd by CD square is equal to 1, which is an equation for ellipse, right? The locus of ellipse. So therefore this point will trace ellipse. So what if I want to draw a a circle? Okay, in order to have a circle, this AD and CD has to be same. How can we achieve that? We can achieve that by choosing the D point, which is a midpoint between C and A. Okay, so that's the point B. Okay, so if I choose this as the point, then this particular point will trace a circle. Okay, so that's about elliptic trammel. Now in this one, just think, what if I fix link 3? Okay, what kind of mechanism we will achieve by fixing link 3? So just think about that, and we will see, we'll discuss with another topic. Okay, thank you.